Our next speaker is Jeff Tansora, and he is a IAB member and the chair of IETF routing group, the chair of the IETF routing group, and the VP of network architecture in FutureWave Future Networks. And the topics of his talk is the critical role of maximum SID depth, hardware limitations in segment routing ecosystem, and how to work around those.
Thank you. Good afternoon, everybody. It's great to see you here. Really to help out the friend, and since I'm chairing a routing working group where TI-LFA work is happening, TI-LFA is an optimization on top of LFA, which finds a free alternative paths. If you're familiar with what extended PQ space is, TI-LFA gives you a path to PQ node. So there's a draft in routing working group you could go look into. Can I please have the clicker? Yep. So I'm going to be talking about the max SID depth, which is a hardware limitation based on what silicon on your routing platform of choice could do. So segment routing, as you've seen, becoming mainstream technology. Many people are using it in production. However, as any other new technology, it comes with its own set of limitations. It's important to know, to understand them, and how to work around those without respinning ASICs. Very important point, as we go through network disaggregation, we see more and more networks deploying white boxes and software that comes from somewhere else. Unless you know which MSD can be supported in a particular box, you might break your network. So it's important to get your hardware vendor to tell you what is it supported, and it's important they provide you programmatic ways, so through API, to question what MSD you support, and then program it in a way it's distributed. So vocabulary, MSD, maximum SID depth, it's an attribute that applies to either link or a router that's distributed through routing protocols that could be distributed through PSEP or BGPLS, northbound to the controller. I'm going to be talking about SRMPLS here. Same limitations are applicable to SRv6, and you could use your imagination. Right. So what's SRMPLS? The SIDs are instantiated as MPLS label, 20-bit entities. If you use centralized programming, you would use a protocol that talks to the controller, usually BGPLS, which will convey all the information in distributed network to the controller. Controller will build a graph, take a constraints coming from an application, and build a path. So MSD is one of the constraints that should be counted when you build a path. The MSD you push down to a device should never exceed capability of the hardware. Otherwise, you'll end up in troubles. So what's important, this only applies to ingress node, since we are talking about source routing, and the ingress router or device is the node that defines the path throughout the network. This is the device that's going to push the step down. So short recap on SRMPLS, prefix SID uses global block, could be either absolute value, so the label itself, or an index where it uses base advertised by neighbor plus offset. Not SID is a type of prefix SID that usually identifies the device itself. So if the SID on the list is a nodal SID, we would use shortest path compute by GP to go to this node. Adjacency SID is a SID that identifies particular IGP adjacency or a link unidirectionally to the next device, gives us ability to deviate from shortest paths and implement traffic engineering. Very important detail. By default, on most implementations, locally significant. It means that in order to look up locally significant SID, you need nodal SID on top, which requires to impose two labels, not just one. And binding SID is a SID that describes particular action on the node that is the anchor node, the node that instantiates the binding SID. Previous talker talked about it. It's a very important concept in MSD. So I'm using open daylight structure. This is what you would see in every modern transport CDN controller. We learned the topology, usually through BGPLS. we build the graph. So NANOG MSD is an attribute that defines how many labels could be pushed at a particular device, either at link level, and imagine you've got different line cards, you've got different generations of ASICs on single device, then link would be important. If it's not, you would just use minimum value to push particular number of labels. So this is how we acquire the topology, the seeds, the MSDs. Seed stack provisioning usually would happen through a protocol called PCEP, which is a protocol between PCE, path computation element, and PCC, which is the ingress node itself. So as you could see, when you compute and path, you should know how many labels, or in IPv6 case, SRHs, the node can push. You should never exceed this value unless you know how to deal with it. And this is the topic of the discussion. So what's the problem? If the variety and depth of MSD is supported, you look at Linux, up to 4.10, they could do only 2. In 4.11, there were improvements, questionable improvements from our perspective. On low-end silicon, 3 to 5 labels. If you take latest Broadcom today, probably you're at 4 labels. You take high-end silicon, Jericho 1, Jericho Plus. Jericho 1 started with 1, today it's 7. So even when running same generation of same silicon, depends on the revision of your microcode, you might have different seeds supported. On the proprietary silicon, silicon built by Juniper, Cisco, number of seeds usually higher, but again, it depends on the age, generation, many details. So the point being, if your seed stack is larger than what's supported ingress node, best case, you'll decline the service. Worst case, you'll actually end up somewhere in the network dropping the packet. So this is a good situation when MSD supported at node A is the same as number of nodes that need to be encoded. This is a fully strict encoding, so you encode nodes you would like to traverse. So we push a seed stack of 5 labels. We pop labels as we go. So far, so good. We reach the destination. Same network with MSD of 3. Obviously, I'll encode 3 labels because this is the only thing I could do. And when I come to node O, which will pop the last label, I'm going to drop the traffic. So knowing MSD when computing the path is crucial if you want to deliver service properly. So I'm going to describe 2 solutions. One of them is stack compression, and it's done on PC or application of PC, where you look at stack and you decide how you can compress, how you can optimize. Solution number 2, based on ability of binding stack to logically create number of subpaths and expand on the anchor node. So the stack compression has been presented in 2016 at a variety of academical events, as well as published to IEEE Explorer. It's based on more efficient encoding. It uses number of topologies. Again, the math behind is described in the documents. I'm not going to go through it. What it shows, however, if you take MSD of 5 and you need to deviate from shortest path, the number of services you could deliver varies per topology. In some cases, it could be as high as 80%. In some cases, it's 37%, as you could see. So unless you can reduce or partition your stack, you won't be able to deliver every service required. So if you analyze the topology versus service requested and average seed depth, you could see that using basic node or link per link encoding, we get to average seed depth of 7, which leaves you out of low-end merchant silicon and would be supported on some high-end silicon and probably proprietary silicon. So what the algorithm does, it compresses the seeds by replacing longest paths by shortest seed, using paths where SPF could be used rather than explicit routing. So again, mass is very well described in the document itself. You could go read it. So what's important, however, as you could see, when you apply the SR-LIA algorithm, you could be at pretty much 95% services that could be delivered to your existing infrastructure. Another way to address it, and it's a simpler way, is to use binding SID to expand to another SID stack. Back to this project, it was implemented as part of Open Daylight. The segment routing code is going to go into FRR base next year. The extensions to Pathman, which is an application, and PCE, is going to be open source next year. So if you're into open source, it's going to be there. So what do we do here? We use binding SID to expand to new SID stack at the node that is the last node within MSD supported. So what's happening? We push 4 label stack, it's maximum we can support, where the bottom label is a binding SID. The important point here, and probably in last presentation you should have seen, binding SID cannot be the top label. It's a local label. It can only be looked up in context node itself. So in this case, binding SID is only relevant to node O, identified by label 9103. So as we go on pop label, we reach node O, and as you could see, node O looks up binding SID. It says, I need to expand it to another SID stack. It pushes to labels that are 900405, and now we can go to the destination. You could build this on pretty lengthy path. You just need to expand and make PCE computing differently. So there's additional constraint, which is the MSD, and you need to count which node is going to be the last in the MSD stack. So from standardization perspective and signaling, MSD is described in 3 drafts. All 3 drafts have gone through IETF adoption and ready for working group last call. So working group last call is procedure in IETF before a document becomes an RFC. Thinking about future, we've created common IANA registry for MSD types across all the protocols, so you don't need to go and change and tweak every protocol. Base MSD is defined as number of labels a node can push. You can define new types, and this gives you the ability to innovate very fast. You think about recirculation, you think about entropy, you think about V6, you just define new MSD type. It could go through IETF in less than a year. You've got new extension that can describe piece of metadata that's of importance to you. So the conclusion, we know there are hardware limitations. Unfortunately, it's an expensive and time-lengthy process to respin new ASIC. Usually it would be somewhere between 18 to 24 months. Doing software computations that helps you to address these limitations is important, and it's possible. So look into your software. We are in a software-driven world, and even with limited hardware resources, you could work around. Working ATF ensures you it's going to be interoperable. There are already implementations. FRR is coding right now. Cisco has planned. Juniper is kind of okay with it, so hopefully they're going to do it. You'll get solutions that's technically sound and interoperable. And get your vendors to implement it, software as well as hardware. Questions?
Rüdiger Volk, Deutsche Telekom. Having your presentation after the V6 oriented one, the question of the MSD comes up for me. I note the coding of the MPLS segment routing seems to be more compact than the V6 version. Just because, well, okay, yeah, the
20-bit and 128.
Yes. Seeing your report about fairly small numbers of instructions that are permissible for MSD, are the numbers functionally for V6 so low that, well, okay, it always burns down to essentially 1?
It's not 1, but it's close. I see some vendor faces. You could talk to them.
Kind of. It's a little bit of a pity, but obviously a consequence of physics. When you use the many bits, I really like the concept of using the IPv6 framework, but if it doesn't work in the end.
So MPLS has beautiful property of stacking, right? You can look up one label in the context of another one. We know how to do it in hardware. We know how to do it in FastPass. And FastPass, remember, you could go fast, you could go deep. If you try to do both, you'll be punished. So the point being, you really need to know what you're trying to deploy. And the use case is one I hit. In my previous life, I tried to build 5G next generation backhaul for optical networking. And we ended up with 3 different site routers doing different MSDs. So unless you understand the limitations, you're going to end up with non-functional network.
Question, I think you touched it broadly, but is the MSD matters for the TLFA in the core?
So if you look at type 0, and this is the base MSD, this is going to be in the RFC, it talks about total number of labels. If you want to distinguish between VPN labels versus transport labels versus entropy labels, it's going to be type 1, type 2, or type 10. It's very easy to define, and it's just a TLB encoding in the routing protocol.
Yeah, that I get. But how many label? Because in some point you said that the label imposition is ingress. But in TLFA context, I need to impose, or also binding SID. My core router has to do the multiple pushes. I don't know, 1, 2, 7, whatever. Right? So we need this information also for the core devices, not only for the ingress.
So there's a reason it's been used in both IGPs and BGP. IGP provide you flooding facility. And since every router floods its information and topology artifacts such as MSD across all other devices, eventually you'll build a graph where MSD is known for every device. And TLFA would be a good example because you have to push additional labels. In the MPLS case, God knows what you need to do in the V6 case. As of today, IETF wouldn't allow you to change the size of IPv6 header.
So you're flooding the information about that through your network. That means essentially the most limited piece of hardware along the pathway is really the constraint point for it, not the ingress device, right?
The beauty of segment routing, only ingress not has full state and has to push full label stack. On transport, usually you would do either swap or continue in segment routing terms, or you would pop top label, look up next label. So usually you are within your limitation unless it's really very old.
If my ingress device has a limit of 7, but the immediate next device has a limit of 2, then sending along to that and it pops off the first one, you're kind of screwed on 5 of your labels, aren't you?
No, you only look up top label and the rest of label stack is treated as data. So you never look up whole label stack.
Gotcha. Thank you for clarifying.
Unless you're trying to do things like NFV and others, where suddenly you need to look up deeper, and this is where MSD comes in help again. You really need to know what your hardware is capable of.
Gotcha. Thank you.
Thank you so much. It's been my pleasure to be here.